integrate from the bottom value to the top value. Which in this particular case, what does it mean? The z goes from 0, right, to this value. But what is this value? This value is going to be 1 plus, this is going to be the value of z on the paraboloid. So that in the Cartesian coordinate system, this would have been 1 plus x squared plus y squared. But now we're replacing this with r squared. So because we are doing the integral in the polar coordinate system, we will actually write it as 1 plus r squared, where it is understood that r squared comprises x squared and y squared. The sum of x squared and y squared. Mm-hmm. Yes? Mm-hmm. That's right. Well, up and down because I have chosen the projection onto the xy plane. Right? So the way I suggest to do the integral is the following. First, let's choose the two outer integrations, the first and the second, right? So geometrically, it means that you are projecting your three-dimensional region, three-dimensional solid, onto one of the planes, one of the coordinate planes. I'm talking now about really the Cartesian coordinate system, but the cylindrical coordinate system is not that far away from the Cartesian, so the same analysis applies here. Right? So the projection here is going to be the disk, right? But in general, it could be square, it could be something else. So that will be taken care of by these two integrations, by the limits here. That's right. The projection goes in those two. And the inner integral is the remaining variable, which in this case is z. So to put the limits here, you have to take one of the points in the projection, in the image of the projection, which is this point, say xy, which actually, because we're doing polar coordinates or cylindrical coordinates, this would have to be recorded as r theta. Right? So this point will be r theta. And we'll have to take the segment along this third variable, which is the z variable, going from the bottom to the top, from sort of the bottom lid to the top lid of this figure, of this region. Which, as I explained, the bottom is on the xy plane, so the z is equal to 0 at the bottom, and at the top, we have to look at the equation of the paraboloid. It's 1 plus x squared plus y squared, which, because we are working in cylindrical coordinates, will be written as 1 plus r squared. Okay? Let me finish the integral and you ask me if you have more questions. So then what remains to be done? What remains to be done is that we have to put also here r and theta. So we have to choose some order in which we will do r and theta. So let's say we put here dr and put here d theta. Because now we are actually, see, once we are here in these two outer integrals, we're actually doing a double integral. We're deciding how to split the double integral into iterated integral. So, and what we're working with is already the image of this three-dimensional object onto the xy plane, which is nothing but the disk, right? So for the disk, we know what the limits are. First of all, we know that it doesn't matter in which order to take r and theta. And second of all, we know that r goes from 0 to the radius, which is in this case square root of 5, and theta goes from 0 to 2 pi. Right? That's because the disk, this disk, is described by, well, I don't even have to write one more time. I just have to add here theta from 0 to 2 pi. And finally, we should not forget to put the function, which is e to the z, and we should not forget to put this factor r. So I'm introducing a slightly different notation from before. Right? Normally, we would write this as e to the z times r times dr d theta, and then we put sort of brackets, and we think about integrating first this with respect to r, and then this with respect to theta, and then, sorry, integrating this with respect to z, then this with respect to theta, and this with respect to r. But I'm writing it in this way, which I think is a little bit more suggestive, that you write the dr, the d theta, and dz, the d of the variable you're integrating, right next to the integral, so you remember which one it is. You see, because if in the old way, you have to put dr, the last one, right? So the last one will get paired with the first integral, the next to last will get paired with the second integral, and so on. This way, it's a little bit more intuitive, so I prefer to write it this way, but you can choose whichever way you like. But I hope that it's clear what I mean. Well, this certainly is not clear, because it says onto, and then it says 0, so let me erase it here, and then write onto. Like this. I think now it should be clear. Okay, any questions about this? No? Yes? That's right. So in fact, I could have put r all the way here. Right. Hmm? Oh yeah. You're right. Right. So I actually did it in the wrong order. So this. Did I do it in the wrong order? No, hold on. No, the order of course matters, because see, the point is that. No, I did it correctly. Who thinks that I did it correctly? Who thinks that I didn't do it correctly? Okay, you guys you failed, of course. No. No. We are here to find the truth, you know. But see, here's the way. I thought about it this afternoon, actually, and I convinced myself this is right. But see, here's the point. The point is, right. So the point is that we are. This is actually it could be very confusing. So let's actually do it slowly. You should not worry so much about the fact that here there is dependence on r in the inner integral. What you should worry about is the fact that there is dependence on r in the limit. So you certainly don't want to put this outside. You see, because you want to end up with a number. Okay. In other words, we can disagree on many things, but there's one thing we should certainly agree on, which is that the integral is a number. Okay? It should not depend on r, it should not depend on theta, it should not depend on anything. It's a number. You cannot possibly get a number if the last integration has a limit which depends on the variable. Okay, so it's not going to work. But more conceptually, the way I'd like to think about this is as follows. And I would like to think maybe in slightly, it could be some more complicated domain. So what I'm doing is I'm projecting, so there's some E. And let's say I want to project it onto the xy plane. But right now, let's talk about just the Cartesian coordinate system. Let's not worry for now about cylindrical and spherical. Even the Cartesian coordinate system, the way I would like to think about integration is as follows. That I have a region in the three-dimensional space, right? And what I do is I project it onto the xy variable. So now, if I have a triple integral over E, where I have f dv, first of all, I split it like this. It's going to be a double integral over d, over this d, over the single integral with respect to the remaining variable, dz. You see, where for each x and y in d, for each x and y in d, you will have some lower limit, let's say L of xy, and you'll have some upper limit, u of xy. Right? So that's what's going to look like. Yes? So then I would just write like, oh, and here, yeah, that's right. So then here I would put dA, like this. Yes? That's right. In the old way. Right. So you want me to write this in the old way? Okay. So this, in the old way, would be 0 to square root of 5, 0 to 2 pi, 0 to 1 plus r squared, right? E to the z, dz, d theta, dr. Oh, I'm sorry, r dr. Yes, very good. Thank you. See, because it's red, so I didn't see it. R dr. Well, usually we write r dr. Yeah, r dr. Okay, fine, whatever. We can put r inside here. Maybe it's better. Kind of keep that. Just put it here. Okay. So then normally we would put brackets like this. Is that okay? Does that make sense? So what I'm doing is just I'm trying to avoid using the brackets and instead just putting the differentials right next to the integral. So it becomes a little more clear to me anyway. But you're free to use whichever way you like. So so this is sort of a new way to write, and the old way to write would be f dz. Well, it's almost the same. dA over d. Maybe like this. So, but the main point which I would like to make is that the first two integrations in the formula. See, it's very confusing because when I say the first integration, do I mean the first integral or do I mean the actual integration you perform? This is opposite, right? The first integral you write is the last one. It's the last integral you write is the first you calculate. Okay, that's right. That's right. So this is the outer. The outer is written first, so that's why it goes last. You see? So you have to figure this out on your own. I guess at some point you have to think about it and have a clear picture because like I said, it's very confusing. What do you call first? What do you call second? Who's on first and right? So the last integration is the outer one, and the last integration corresponds to the projection of your three-dimensional region onto the plane. Okay, that's the point. All right. So having established that, let's evaluate finally this integral. So what do we get? We get 0 squared root of 5, 0 to 2 pi, and then here we get r times e to the 1 plus r squared minus 1, right? Then you get dr. This integration just gives you 2 pi because the integrand does not depend on theta, so you just get 2 pi times r e to the 1 plus r squared minus 1, right? And finally you integrate over r, and so here you want to use you want to change variables. So I'll just write the answer. So you get 2 pi is an overall factor, and then you get 1/2 e to the 1 plus r squared minus 1/2 r squared between 0 and square root of 5, right? And so the answer is 2 pi times e to the 6 minus e minus 5. 1/2. Well, because 1/2 and 2 get cancelled, so you get e to the 6 minus e, and this guy gives you 5. Right, so that's correct. Okay? Yes? It's pi, that's right. So like this. Thanks. Okay, cool. So we good with this? Yes? Is it universally accepted that? Are you talking about this formula or this one? This? You mean this integral? Yes. But I'm not sure I understand what the question is. Which line, first of all? This one or this one? Yes. Here. Are you looking at the left-hand side or the right-hand side? Sorry. The question is it okay to put dr before the function of r? Oh, okay. The answer is yes. It is okay. I'm suggesting this notation. In the book, it's not used, right? But as a practicing mathematician, I can assure you that a lot of people use that. You know, it's certainly interchangeable. They do commute, in other words. It doesn't matter which order you write them. It's a more interesting point whether this guy's commute. You know, whether it is important how you write dr d theta or d theta dr. This is a much more subtle point, which I'm not going to get into too much. But certainly dr you can put on the left or on the right of the function of r. So that's no worries here. Okay, let's move on. So the next one is called spherical coordinates, and it's a little bit more interesting. Sorry. Spherical coordinates, and of course the question is right away, why are they called spherical coordinates? Because they should remind you of a sphere. Okay, as you will see. So let me actually keep this. Let me keep this picture. So spherical coordinates work in the following way. Suppose you want to invent a coordinate system in which it is a sphere which gets the simplest possible equation. You see. So in the cylindrical coordinate system, it is a circle that gets the, say, in the polar coordinate system, it is a circle which gets the simplest equation. R equals a constant. That's the circle of a given radius. In the cylindrical coordinate system, the simplest equation is the equation for the cylinder. Okay. R is a circle in polar coordinates, because R is a cylinder in the cylindrical coordinate system, cylindrical, in 3D, this is in 2D. And now I want to have some variable rho such that this equation will give me a sphere. And that's called the spherical coordinate system. And that's in 3D. So that means that this rho should really be the distance from the origin of my coordinate system to my point. Because the sphere, sphere with the center at the origin. The sphere with the center at the origin of radius r capital, this one, is going to be the set of all points such that the distance from the origin to my point is given by this number r. Let's say square root of 5, like in the previous example. Okay? So note that this is not the same as r in the cylindrical coordinate system, because r in the cylindrical coordinate system is not the distance from the origin to this, but rather it's the distance from the origin to the projection of my point onto the xy plane. So that's not the same thing, right? So you see right away that this is not the same coordinate system, and sure enough, this simplest equation, rho equals a constant, describes not a cylinder, but a sphere. Okay? But now, so now I got the first variable of my spherical coordinate system. But that's not enough. I need 3 variables, right? Because I'm in a 3-dimensional space. So I need to complete this row by 2 additional variables, 2 additional degrees of freedom, if you will, so that I could give each point a unique address by using those 3 coordinates. What are they? So the standard, there are different ways actually to do it, but the standard convention which we are using in this class and in this book is the following: that we measure 2 angles. In addition to row, we measure 2 angles, and the first angle is exactly the same as before. It's theta. It's the theta of the cylindrical or polar coordinate system. Okay? And so we need one more, and we find this one more by measuring this angle, and we call this phi. So the spherical coordinate system has 3 coordinates: rho, phi, and theta, where only one of them is part of the cylindrical coordinate system. This theta is part of the cylindrical coordinate system, but the others are new. Okay? So by the way, notationally, phi sometimes is also is written like this. It's the same thing. So I find it easier to write phi like this, but when you type, for example, and in the book it's written like this. So you can use whichever notation you like. So rho, phi, and theta. The first step, of course, is to express the usual coordinates, the Cartesian coordinates, in terms of rho, phi, and theta, and to see that indeed these coordinates are determine the points in space, and also to see what the ranges are. So what is the formula? Well, what we can do is we can use the old formula, which is r cosine theta, and then note that r is equal to rho times this. This is equal to rho times the sine of this angle. See, the point is that this has the right angle. This is the triangle. This is the triangle which has the right angle, and this is phi. So you can find this distance, which is r of the cylindrical coordinate system, by taking rho and multiplying by the sine of this angle. So this is rho times sine of phi. And now I substitute this in here, and I get rho sine phi cosine theta. Yes. Which axis is phi measured from? It's measured from z, right? So I did not put labels, but I should. Yeah, that's why z, it's standard phi. Another question. Rho is not. It does not belong to any plane a priori. It's in space somewhere, right? It's just that I have a point. It kind of floats around like this, right? Wiggles around. It's not. It doesn't belong to any particular plane. It's free to move, right? Because our point is free to move into space, and so the segment connecting our point to the origin, it does not necessarily belong to any plane. Which one? This triangle? It has the right angle here, because this is a projection. I don't know if it looks like a projection. It looks a little bit. It's a little bit crooked, I guess. It should be more. Should be a little bit more parallel to the z plane than what I made it look like. Is that better? Slightly. Okay. So this is a perpendicular which we drop from this point, from our point. This is our point. We drop it onto the xy plane. So I guess the rest should be clear. Any other questions? Yes? That's right. The theta always taken from the x-axis for the projection. Everything is a little bit not straight on this picture. So this is r. This is old r, which is not. This r is not part of the spherical coordinate system. It's part of the cylindrical coordinate system. The reason I have drawn it, I've written it here, put this label, is to make a connection between the spherical and the cylindrical coordinates, and also to simplify the derivation of the formula for x, y, and z. Because I do it in 2 steps. I first recall the formula for the cylindrical coordinates, which is really the same as for polar coordinates, and then I just substitute r equals rho sine phi. And then I do the same for this y variable. And then z is, what is z? To find z, we have to complete this to a rectangle. I'm sorry? It should be sine theta, that's right. Thank you. All right. And to find z, I have to use another right triangle, which is this one. Yes, again, I didn't do it very well. Maybe more like this. Okay. So this is right triangle. This is phi. So z is rho times cosine phi. So if you visualize this picture, you see that you don't have to memorize or write on your cheat sheet the formulas for the spherical coordinates. It's very easy. You have to remember polar coordinates, of course, but I mean, if you don't remember polar coordinates, then it's like remembering your phone number in some sense, I think. So if you remember polar coordinates, then the spherical coordinates are very easy just by memorizing this picture, visualizing this picture. Okay. What are the ranges? So rho is like r. Rho is a non-negative number. Although for r, if you remember, we had a certain convention in polar coordinates. We sometimes allowed r to be negative, but in spherical coordinate systems, that would make things too complicated. So we don't do that. So rho is non-negative. Theta is just like in the polar coordinate system or in the cylindrical. It's between 0 and 2 pi. And what about phi? What are the ranges for phi? 0 and pi, exactly. Because you can go. So if this is a vertical, the z-axis, you can go all the way down to pi. But if you go more than pi, then you can sort of approach it from a different direction, and it will be less. From that direction, will be less than pi. So that's what we do. So it's going to be from 0 to pi. You see what I mean? Yes. That's right, from the vertical. So in other words, what I'm saying is, let's say, so this is the z-axis, and this is the origin. So you have let's suppose that our point actually lives on the yz plane. So and let's start rotating it.